Okay. Good morning, all. Am I audible? Yes. So today there is some change in the schedule. Most probably this and the next lecture will be AA. I will be conducting that. Okay. So uh, so we'll start today with the approximation algorithms. Okay. So let us understand what is the motivation behind learning approximation algorithms. Okay. So many problems, okay, uh, in real life belongs to category of hard, okay, of being hard. Formally, what is a hard thing? That is a different thing. But for us, what would be the hard problem is some problem which may take, I mean, uh, too much time, okay, when the input instance size goes larger. Okay, so when n, we generally use n. What is that? Is an input size, right, in an algorithm. So when that could be different meaning of n. For example, if you are talking about a graph problem, the number of vertices and number of edges could be the input size. Okay, for sorting, n is different. So when n increases, okay, we are actually interested in what is t of n. Okay, and that if this t of n is, I mean, significantly higher when n increases very high, in that case, what will happen? The program takes too much time, okay, and I mean, that is not very efficient. So efficiency decreases. Those type of problem, informally, we would treat them as a hard problem. So all of you must be knowing that is what is T. Okay, so that is called compute. There is a separate subject called computational complexity theory. Okay, and in this computational complexity theory, they have defined various categories of problem. Okay, there are so many actually. The more popular one are like P, NP, NPC, NP complete, and then NP hard. That probably you have heard the names, and you will learn in detail. Okay, MSB sir will start that soon from the next lecture. Okay, so for us, P means efficient. In P means those problems which has efficient algorithms. Okay, okay, those kind of problems, okay, belongs to a category of P. We know this, and NP means uh, they can be efficiently. You can verify those problems. Okay, verification is possible. Okay, but uh, we don't know about efficient algorithm. Okay, or about efficient algorithm. So that kind of thing. Okay, verification means, so if you are given output, you can check whether that output is correct or not, or in an efficiently way, means in polynomial type. Okay, so if you are having a vertex cover, so given an answer of a vertex cover, you can quickly check out from the graph, is this really a vertex cover or not? Vertex cover we already discussed, right? So that way. But to find a vertex cover in general is a difficult thing. So those belongs to category of NP. Okay. So even nobody can prove that it is not having an efficient algorithm, or even don't know whether it exists or not. Okay, so those kind of problem belongs to the category NP, where verification is very simple. Simple means in polynomial time, while the actual computation or to get the answer is very difficult, which is a NP hard or NP complete kind of thing, right? So, so to get rid of this type of issues, right? Because many times we need a solution, okay, but we don't know the solution. So what will have? So as I mentioned, many problems of practical significance are NP complete. Don't worry about formal definition of NP complete. Right now, it is sufficient for you to know that they are too time consuming when input size grows. Okay, and those problems are too important that we cannot just abandon them. Okay, so we must require some way to find the solution in polynomial time. So this is our objective. There are hard problems which cannot be solved in polynomial time. Okay, that is efficiently on larger inputs, but we somehow we want an optimal sorry, somehow we want some solution. Okay, so how can we get rid of this situation? Because we cannot just ignore those problems. Those problems are very much useful in practical life. Okay, so there are at least three ways to get around this NP completeness. Okay, there are three ways. This is mentioned in the Corman book. Okay, there are three ways, at least three ways. Many could be possible, at least three ways are there. Okay, the first is you separate out the case where the inputs are small. So what does this first point mean? Many times, even if the problem is belongs to the category NP complete, you will not realize it is a NP complete. Why? Because if you make a program, you just make a program with a small graph of 10 vertices maximum. Okay, a few edges. Okay, you won't realize that it is actually indeed difficult because it will run very fast on your CPU, right? We'll get the result. Okay, so many times, okay, or most of the problems when the inputs are small, okay, algorithm with exponential running time is also perfectly satisfactory, right? Like, let me give you example of that. 01 knapsack using dynamic programming. You must have, okay, must have learned and must have implemented. Okay, yes or no? Yes, right? So this 01 knapsack is kind of a problem that you have implemented, and you see you make the table and fill the entries of the table. Okay, gradually by row wise you fill the entries from already existing values. You reuse them and fill up the table, compute something, and maximum profit you put in the table. So that way you must have done. So you must be feeling that it is just two loops, right? And within which you have some statements. So you must be feeling that it is an easy problem because it just has a two nested loop. So, I mean, it could be n into an n square kind of thing. It's not actually. When the number of items increases for the knapsack problem, okay, this problem is indeed very difficult to solve. Even using dynamic programming and all those techniques, backtracking, dynamic programming, depend on, yes, very correct, Vishru, depend on input size. So if the capacity of knapsack is large, then what will happen? Those many columns will be added is large, or then what will happen? It will increase the number of columns in the table. Am I saying correct or not? Yes, because you have the as many columns as you have the capacity. So it will increase the number of columns. Number of columns increases means number of cells increases. Cells increases means computation increases, right? Even if number of items increases or number of that is capacity increases, anyways, it will be very, very difficult to solve for even n is equal to 100 or 1000. It is also not very big instances. Takes a significant amount of time. Okay, so so it looks like it's easy because it runs into loops, but it is not actually that easy. It's one of the hard problem to solve. Okay, and many other problems can be solved if you solve this 0 1 napsecond polynomial time. Okay, well, that is a big question. Okay, so so yes, so this one, when the inputs are small, it's perfectly fine even if you have an exponential running time algorithm. But when it grows larger, it becomes a difficult. So that means I want to say, if you have a smaller input size, you can use that exponential running time. It's perfectly satisfactory. Okay, but this is not always the case. So let us go to the second point. Okay, you must be able to isolate important special cases, right? So that we can solve in polynomial time. So even if it is exponential running time algorithm, you could have in some problem, some algorithm, special cases that it would run faster if you have this type of input. Those are the special cases. I don't give you the example for the same, but there are, this is possible. Okay. So that is also that is, but always you don't have special cases to solve. Okay, and that is also not going to work. So what is a way, third way? The third way is we may come up with approaches. Remember, we may come up with approaches. So what do you mean by approaches here? Approaches means an algorithms. For example, greedy approach could be there. Okay, approach is there, or it could be because greedy generally has a polynomial time solutions. Almost all greedy algorithms you studied are polynomial. For example, prims or Kruskals or fractional knapsack or making change or so many, right? Like Huffman coding and so many things. I mean, so you can do in greedy way. I mean, that would be perfectly satisfactory if you are not interested very much in optimality. You are not worried about optimal answer always. In that case, it's okay if you have some greedy approach to solve hard problems. Okay, provided you are not too much concerned about optimal solutions. Okay, it's not desirable to have an optimal solution. It's okay if you have a suboptimal solution, okay, or near optimal. Okay, you are comfortable with a near optimal solution. Then only, okay, because always, so this is one approach. Another approach could be linear programming approach. So you create a linear program. That's why we covered linear programming first in the second sessional, so that we can use that idea over here. So linear program could be second approach. So what we can do is we can create a linear program out of it. And for linear program, various algorithms are there. Remember, don't there are so many algorithms for solving linear program. You only know one, okay? No, Priyank, hard problem does not mean it has no solution. It has solution, but definitely it takes a longer time, exponential time, to have a solution. See, no solution, those kind of problems are different one. Okay, there are some problems like Turing's halting problem. Okay, those type of problem, undecidable problem are there. You will learn these things in future. We don't require those things over here, but there are some problems. Okay, I mean, for which we cannot decide whether there is a solution or not. Okay, not decidable problems are there. But I am not talking about. I am not saying that there is no solution. I am saying there is solution. To get the solution, it takes a lot of time. Means to get the optimal solution, it takes a lot of time. Okay. And as I mentioned, and as the input increases, it takes a lot of time. That is the important thing to remember. Okay. And so one approach could be greedy approach. Okay. One approach could be linear programming approach. In linear programming also, you know, I was talking that simplex algorithm. Remember, simplex algorithm, the normal simplex algorithm, sometimes even it is where I mean taking lot of time. Okay, but yes, you can say 95% of the time on the inputs, it will perfectly work in polynomial time. Okay, that's why we can trust the simplex one. But there are other algorithms like interior point methods. You see that algorithms are there, interior point algorithms to solve the linear program. You see, we have completely ignored interior points of the feasible space, okay, while covering simplex, because we know that the solutions are in the corners, right? Or intuitively, I explained you why it is in the corners. But there are other algorithms which takes care of interior points and try to find the corner points. Those are called the interior point algorithms. Okay, so there are so many varieties of algorithms to solve even a linear program. You know only one, that is a simplex one. Okay, so because it's a much more popular and practically used simplex one, that's why. And most of the time works in polynomial time. Okay, so this is another way. So greedy approach, linear programming based approach. Okay, so these are some of the ways, okay, to, or heuristic based approach could be there sometimes. Okay, so these are some of the ways or approaches, okay, for the third point. So we may come up with the approaches to find near optimal solutions. Okay, but remember, don't say the best case, because whenever we do analysis, it is important to touch the worst case, right? So you take your input which works fine on your algorithm and you say my algorithm works very well. Okay, it should not be the right way. It should work in general very good. That is on an expected, that is expected. We have seen expectation, right? On expected running time, it should be very good. Or in a worst case also, it should work very well. But you see, I compromise one thing, that is optimality, and I am now interested in near optimal solution. Okay. Now you will say, not always it will work, but most of the time, near optimality is also going to find. Why? Why? The question is because they are efficient. Okay. We compromise optimality, but we get efficient answer, polynomial time algorithm for that. Okay, so that's why we call an algorithm that runs in that runs near optimal solutions. They are also called suboptimal solutions and approximation algorithms. This is a term you have to remember. What is an approximation algorithm? Okay, it tries to find a polynomial time solution for, or rather efficient solution for the hard problems, which may not give you the exact or optimal answer. For example, if you solve 0-1 knapsack using dynamic programming, you will get exact answer, optimal answer, maximum profit you will get. Okay, but it's not going to work well when input size grows larger. So what we can do? We could have some approximation ideas like fractional knapsack and other things, by which I can somehow convert and translate and get back the answer. Okay, so this chapter represents the polynomial time approximation algorithms for several NP-complete problems. We'll see various NP-complete problems. Now you see, you have to pay attention in both the portions, mine and MSB sir, to completely get the picture, right? Because the hard problems and the theory of hard problems you will learn there, while how to solve that hard problems approximately you will learn here. So if you focus on both the things simultaneously, it would be you will get the entire picture. Okay, so both the ideas should be there, theoretical ideas and practical ideas. Like this could be a practical idea where I want to implement something in polynomial time. Okay, there it would be completely theoretical approach where you will study about lot of problems, new problems, why they are hard. Okay, the reasons, proofs of that. Okay, it seems very good, but there is one thing. What is an issue that I have to prove that it is a near optimal? How can you say that it is near optimal? Just I say and you believe? No. You have to actually prove. And this is a very important thing. Okay, you have to prove that it is nearer to the optimal answer. But what is the big thing? You don't know optimal answer. Still, you have to prove that your answer is nearer to the optimal answer. Yes or no? Because if we have optimal answer, we'll not waste our time in finding an answer, right? Am I saying correct or not? Yes, right? If we have optimal answer, why should we waste time in approximation algorithms? So we don't know the answer, optimal answer, right? Still, I have to prove that my answer, approximate answer, is nearer to optimal answer. And that is the interesting thing that we will see. So without knowing the optimal answer, we should prove that our answer is nearer to the optimal answer. And this is actually a tricky and difficult thing in approximation algorithm. So just a design of an algorithm is not sufficient. So you can design algorithm for some hard problem. So somebody could come up with a very nice algorithm. Okay. But the algorithm cannot be accepted without a guarantee of nearness to the optimal answer. So you should also come up with a proof, right? And which is difficult, right? To prove in general. Also come up with a proof that your approximate answer, okay, answer is nearer to the optimal answer. Okay, near to optimal answer. And that near also has the different context. How nearer? By what factor it is near? Are you getting what I'm trying to say? Yes. Right now, there are many students, right? Yes. Others? Yes. Okay. Those who are at home? Okay. Fine. So now, fine. So let us see the first idea. The first idea is to define a concept of approximation ratio. Approximation ratio, which I should write as a rho, the Greek symbol rho. Okay, let us try to understand what is the meaning of this. So, the performance ratio for approximation algorithms. So, algorithm for a problem has an approximation ratio of rho n. Okay, if for input of size n, so remember you have some algorithm, input size is small n. The cost C of the solution produced by the algorithm. So there is some cost C, right? That means it could be the number of steps or computational time or complexity. The cost C of the solution. So algorithm will produce a solution. What is the cost of that? C. Which algorithm I am telling? Approximation algorithm. So whenever I am talking approximation algorithm, okay, the cost of that I say small, I mean this C, just the C is a cost of approximation solution. So our solution returned by approximation algorithm. Okay. And what is it then C star? You can see there are two things, C and C star. So C star is an optimal solution, a cost of the optimal solution. So this C is a cost of the approximate solution. C star is a cost of the optimal solution. And you see something, I have written maximum of C upon C star, comma, C star upon C, some less than equal to rho n. Okay, don't worry, we will see this. What is this? But what we do is, this is a ratio, C upon C star upon C. These are the two values. And I find maximum of that. And that should be less than or equal to some rho of n. So now you can see rho is like a function of n. Okay, as n means input size. So if rho n is like constant, like K, it is very good actually. This is desirable. Okay, which means it doesn't depend on input size. But if rho n is, let's say, log n, okay, which means the ratio grows with n. Okay, when n increases, log n increases, right? It grows with n. So many times this constant is desirable, but we are not always lucky to have a constant ratio, right? Some problems can have constant ratios, some problems cannot have constant ratios. So what is a rho n? Rho n is called an approximation ratio. And that we should prove. So suppose, let me cancel this rho n and let me write 2, which is constant, right? Let me give an example. That will be clear, Priyank. Don't expect exactness from beginning, because it will be much more clearer when we take example. Okay. So let us say C upon C star, okay, is let's say C upon C star is less than or equal to 2. Don't forget about maximum and everything. C upon C star is less than equal to 2, where 2 is what? Rho of n. It means rho of n is equal to 2, means ratio is 2. Which means C is less than equal to 2 times C star. Okay, now can you interpret this? Can anybody interpret this? C less than equal to 2 times C star. C star is an optimal answer. For example, C is your approximate answer. So what I'm trying to say? What I'm trying to say by this? Am I trying to say that my approximate answer is 2 times, maximum 2 times the optimal answer? Or it could be less than that also. Yes, very correct. Rishi is, if you forget mathematics, this conclusion derived is approximation is nearer to the optimal answer. With the factor of 2, it is nearer. Okay, so maximum it can, so maximum C is could be 2 times C star. Okay, which type of problem do you think I am talking about here? Minimization or maximization? If I am taking the ratio as C upon C star, remember I have 2 types of ratio. Sometimes I will take C upon C star. Yes, yes. Answer is correct, Yash. Why minimization? Very correct. Because when I am minimizing, okay, optimal answer we have the minimum one. And the approximate answer can go beyond actual minimum. So how far it can go from actual minimum? Okay, so I'm saying maximum C can take is what? 2 times C star. Okay, so actually we want to minimize the cost, right? So C star is an optimal answer, which is a minimal answer. So C star is minimal answer, let's say. Okay, and C is approximate answer. But this approximate answer should be also somewhat nearer to that. So what I'm trying to say is C is less than equal to 2 times C star, which means C is either 2 times the minimal answer, or it could be 1.5 is into minimal answer. It could be exactly equal to minimum answer, or I mean, then it's very good actually, but that doesn't happen, right? So are you getting what I'm trying to say? Yes? Yes, okay. Yes, hey, Zuzar, Harshil. Yes. Fine. I hope you understand, right? So that I progress. Okay, so that way. Okay, but same way. Okay. Suppose I am talking about maximization problem, where some optimization problem is there, where I have to maximize something. For example, in 0-1 knapsack, where I want to maximize my profit. Okay. So in maximization problem, okay, which type of ratio you should consider? Should you consider C upon C star? Yes is saying C star upon C. Shail is saying yes. Priyank, do you agree? C star upon C? So remember, in case of maximization problem, C star is maximum answer, maximal answer, for example. Maximum valued answer, right? This is just a notation. C star is a maximal answer, right? Because it's an optimal answer. Optimal in the case of maximization is maximum answer, right? And if I say C star is less than equal to 2 times C, which means C is greater than or equals to C star by 2, okay, which means the C star by 2 is less than equal to 2, which means C is greater than or equal to C star by 2. Okay. So what do you conclude now? Yes, Yash, can you write? C star is maximum answer. For example, let's take an example. C star is, let's say, 200. And the C you are getting is 100. So then in that case, C star should be higher, right? Because C star is a maximal answer. So C star by C, if you do, it is exactly 2. Okay. But if you get C is equal to 125, okay. I mean, sorry. If you get a C is equal to, let's say, 80, okay, and what it will be? It would be, the ratio would be 80 by 200. So what we just do is C star by C, and then that would be the ratio. Are you getting? See, I always want it to be less than equal to something. So whenever I say C star by C is less than or equal to 2, what does that mean for maximization problem? Maximization type of problem. If I say C star by C is less than equal to 2, means, yes, can you take conclusion? Can you make conclusion? C star is maximal. What else? C star is should be higher. So yes, very correct. C is less than C star. Okay. Yes. The point Shail got is very correct. Let's see what is happening. Okay. So for maximization problem, the solution C, optimal solution is C star, and we definitely know the optimal solution for maximization problem is greater than equal to the approximate solution. Okay, which means that definitely both are greater than 0, assuming, but cost of the solution produced by approximate algorithm, C star. Cost right now you assume is a profit kind of thing. Okay, so C star is a maximum value, optimal value. So what is this ratio? I don't want a ratio less than 1. Remember, I don't want a ratio less than 1. So if you do C upon C star, it is less than equal to 1. So that is not going to work, because I don't want a value less than equal to 1. I will tell you why. Okay. So I have to compulsorily take what value? C star by C. Okay, because C star is higher, C is lower. So in that case, C star by C is greater than equal to 1. Okay, so C star by C gives the factor by which the cost of an optimal solution is larger than cost of approximate solution. Okay, so it will be greater than 1. Most probably it is not 1 also, because so C star by C for maximization problem, okay, gives idea, okay, of uh, how that approximate solution, okay, is uh, I mean nearer to the optimal solution. Okay, so this gives you a factor, like it could be 2, which means maximum is 2 times the approximate answer. It could be 3, then maximum answer is 3 times the approximate answer, and that way. Okay, yes, is this clear, Priyank? Yes. And similarly for minimization problem, remember, where we want to minimize something, this could be the minimization, C star would be minimum and less than equal to C. And again, I remember I told I don't want a less than 1 value. Okay, so what I will do, I will again find C upon C star. That would be a ratio, because C star is less than C, okay, which means C is greater than equal to C star, which means C upon C star is greater than equal to 1. Okay, so C upon C star is ratio for minimization. C star upon C is a ratio for maximization. So in general, if I want to write without considering whether it is, yes, that, so that we will see. Okay, how can I explain you without actually going through an algorithm and proof? Okay, that how we'll do that. Okay, so that is not possible at this moment. Okay, you will learn, definitely you will learn in a proof. Okay, so without knowing a problem, okay, whether it is of maximization type or minimization type, in general, if I want to write a definition, so what I should say is maximum of C by C star and C star by C. Okay, whatever is maximum, because one of either C upon C star or C star upon C, one of that will be greater than 1. Okay, yes or no? At maximum of that, at least one of will be greater than 1. So I will compare this maximum value with something called as a ratio, which is a row of n. So I will prove something like this, that uh, maximum. So in general, this is a definition. But remember, for you, it is sufficient to, like if it is a minimization problem, you find C upon C star less than equal to rho of n. If it is a maximization problem, you find C star upon C and compare it with rho of n. So you need to actually prove that it is less than or equal to some rho of n, which is a ratio. Okay. So for we will see that vertex cover is having approximation, and that algorithm has a ratio 2, which means optimal answer. So see, it's a minimization problem, minimum vertex cover. Okay, don't worry if you forget what is vertex cover, I will revise that, but it's a minimization problem. Okay, so I will take a C upon C star. Okay, and I will prove that C upon C star is less than equal to 2. So means approximate solution can be maximum 2 times the optimal solution, because we are minimizing, right? Approximation solution cost is at most 2 times the cost of optimal solutions. So, so this is a constant ratio, which is very good. We will see this, we will prove this. Okay. But for some problems, as I mentioned, ratio grows as a function of n. So there is some problem called set cover. We will see that again. But for that problem, this this you know, right? For minimization problem, you should prove like this: C upon C star should be less than equal to rho n. For maximization problem, you should prove like this: C star upon C is less than equal to rho n. So in general, max of this should be less than equal to rho n. Okay, in general for any type of problem. And we say what? Rho n is what? Approximation ratio. So rho n is approximation ratio. So what I'm saying is set cover problem is there where ratio is a function of n. It's a log n. We will see that ln n, log n. So it's not that good because if the ratio is logarithmic of n, it would increase with n. Okay. So it's not a constant is desirable. So remember, many times we focus on constant time ratio. So as far as possible, you should design an algorithm with a constant ratio. So we have exact guarantees like C is 2 times C star or 3 times C star or 4 times C star. Even if it is 10 times C star, it is okay. But 10 is fixed. Are you getting what I am saying? Why it is advantageous? Yes. Yash, Keval, Priyank, Shail. Okay. Okay. So now I want to add one more thing. And that thing is why ratio can never be less than 1? Yes, this question can be there, right? Why can not be the ratio less than 1? Let's say for minimization problem, assume, right? It is not possible, but assume that approximation ratio is less than 1. Okay, can you tell me what will happen in that case? Approximation ratio for minimization problem is less than 1. What does that mean mathematically? What is approximation ratio for minimization problem? I mean, C by C star or C star by C? Which one? C by C star. Very correct, Kushal. Yes. Okay. So let us assume that approximation ratio is less than 1, which means C upon C star is less than 1. What does that mean? What does that mean? C is less than C star. Yes, Kushal. What is an interpretation of that? C is less than C star? Yes, Sail is also correct. What is an approximation, Shail? Which means approximate answer is even better than optimal. Is it possible? Is it possible? No. C is less than C star, which means approximate answer is even better than the best answer, which is not possible because the best is best, right? So this violates the assumption that C star is optimal. Yes or no? This violates assumption, okay, that C star is optimal or minimal rather. Okay, in this case, it's minimal. Okay, which means this is not possible. Am I saying correct or not? Yes, Keval, Rishi, others? Yes. Offline students, if you are there listening, you can also reply, right? Okay, fine. Uh, so approximation is less than yes. So why can it not be possible? Which contradicts the fact that minimization problem, it should be C star, it should be less than equal to C. It contradicts the facts, right? Same way for maximization problem, if I assume the ratio is less than 1, which means C star, for maximization, it is C star by C. So C star by C is less than 1, which means C star is less than C, which means optimal cost is less, I mean, optimal answer is less than approximate answer, which also contradicts because C star is a maximal answer. Okay, so for both the types of problems, ratio cannot be less than 1. So remember this fact that rho n is greater than equals to 1. Okay, the ratio is greater than equals to 1. Let me add one more point. There is no point of saying ratio is equal to 1 also. For some cases, it would work, right? For few examples, for few input instances, you can get a ratio 1. But in general, you will not get ratio 1. Okay. So ratio 1 is also impractical. Why? Because rho n equal to 1, which means C and C star are same. Means optimal solution, approximate solution are same, which means approximate algorithm always returns exact solution, which is not very much practical, right? If it is like that, you must be a $1 billion winner, because you must have found every problem solution approximately, but it is in polynomial time, which means you have proven P is equal to NP. Am I saying correct or not? If you get every problem solution approximately, but in polynomial time, but that approximation is exactly equal to optimal, which means you have solved this $1 billion problem, P is equal to NP. Am I saying correct or not? Yes, right? So which is not possible. So normally, okay, we write this rho n is greater than 1, and which is very reasonable, very correct. As I mentioned, rho n can be constant, rho n can be function of n. Okay, if rho n is constant, it is a better approximation strategy. So remember, what are the takeouts from this discussion? One thing, approximation can be done in many ways. Remember these points which I am taking. It can be done in many ways, like using greedy, using linear programming. Okay, you have to prove that your approximate answer is nearer to optimal answer without knowing optimal answer. That is hard thing. Okay, so which requires too much effort. Okay, because no one will accept the algorithm without a good approximation ratio. Second takeout, for minimization problem, you should have a ratio like C upon C star. For maximization problem, C star by C. The third takeout, the ratio can never be less than 1 and can also not be 1 in general. Okay. You can have few examples where it is exactly 1, but for all inputs, you will not get such situation. What is an advantage? If you are having not optimal, near optimal, what is an advantage? The only advantage is we are having efficient solution. Less time, probably in less space, probably. Okay, we get an answer. That is the only advantage. But still, it is acceptable because many real-time problems, it's not necessary we must have an optimal answer. Okay, if we have, it's very good. But if we don't have, still we will accept it because we have a finite time. We want in a finite time a solution which we would take and go ahead. Okay, so these are the three very important things. Okay, let me ask you before ending this. Okay, let me revise vertex cover, because in the next lecture we will start with the approximation algorithm for vertex cover and its proof. Okay, of ratio is having 2. Okay, remember, for same problem you can have 3-4 approximation algorithms. Okay, I want to just mention you a vertex cover problem. There are 3 approximation algorithms, all having different ratios. Okay, for example, the first so it could be many algorithms, but I would say there are 3 well-known approximation algorithms for vertex cover. One is using randomized way. So I forgot this way: linear programming, greedy, and randomized way. And that's why our syllabus is, coverage is like that. You learn first randomized thing, then linear programming, and then this. So you know better everything. So randomized way. Okay, then there is a second, using linear programming also you can find the approximation algorithm for vertex cover. And the third, there is also a greedy one. So there are three different algorithms. Okay, but randomized way, the first way has ratio 2, which is very good. Okay, compared, and linear programming also has the 2. Greedy has not a ratio 2. Okay, in some examples. So I mean, so I want to just say that it's not that there is just a one algorithm possible for approximation algorithm. There could be many ways to write approximation algorithm for the same problem, provided and they have different ratios. Then we can compare actually, and we can find the better one. Okay, just I explained, randomized one will be the very good one for vertex cover. Okay, before ending, can somebody define quickly what is vertex cover? If you forgot, what is vertex cover? It's a graph V comma E. And what is a vertex cover? Is it a set? First of all, is it a set? Vertex cover is a set. Yes. Yes, Kushal. Whose set? It's a set of what? Yes, set of vertices. Very correct. How? Yes, what is the constraint? Keval, Priyank, Rishi. Which vertices? Such that? Yes, very correct. Such that it includes at least one endpoint of every edge. At least one endpoint. So from every edge, at least one of the vertices. Every edge has two vertices, right? Two endpoints. So at least one vertex of every edge should be there in a vertex cover. Okay. So maximum vertex cover could be all vertices, right? You take all vertices in a graph, that would be a vertex cover, right? But that is not a good thing, because we want a minimization type of problem, that is minimum vertex cover. Shortly, you will learn that minimum vertex cover is actually NP-hard problem, and corresponding decision version is NP-complete problem. Okay. Same way, independent set is also a hard problem. Maximum independent set is also a hard problem. Okay. So let me end here. First, vertex cover of undirected graph is a subset of vertices such that if u comma v is an edge, that means there is one endpoint u, one endpoint v, then either u is in a v dash or v is in a v dash, or both can be there in a v dash. What is a v dash? V dash is a vertex cover, is a subset of vertices. And what we are interested in is a minimum vertex cover. Okay, and remember, this is a very well-known hard problem. The proof you will learn. Okay, okay. With this, I end here. We'll continue in the next lecture. Thank you.